morning to all of you. On behalf of the organizing team, METASOFT 2022, I welcome you all to this keynote session. Today is the third day of our international workshop and this is the last day. Today our keynote speaker is Professor Bhabani Prasad Sinha. Let I introduce Professor Bhabani Prasad Sinha. Professor Bhabani Prasad Sinha, currently working as Distinguished Professor in Sikha Anusandhan deemed to be University, Bhubaneswar. He first joined the Faculty of Electronics Unit of Indian Statistical Unit Institute ISI Calcutta in 1976, where he became a professor in 1987. He served as the head of the Advanced Computing and Microelectronics Unit during 1993 to 2010. He was the Dean of Studies of ISI during 2010 to 2012. He was an Indian Space Research Organization ISRO chairperson in IIT Kharagpur during 2000. He was an Alexander von Humboldt Fellow of Germany. He received many awards and honors in recognition of his excellent academic performance and outstanding research contribution. The most notable of which includes MT Single Memorial Award for the Indian Science Congress Association in 2012, handed over by the Honorable Prime Minister for his significant and lifetime contribution to the development of science and technology. Homi Bhabha Award of the University Grant Commission UGC India 1998 for his outstanding contribution to applied science. Ramlal Wadha Medal from the Institute of Electronics and Telecommunication Engineering India for outstanding original contribution in the field of electronics and telecommunication engineering during the last 10 years, 2012. Faculty Excellence Award of Clemson University, USA. Eminent Engineer Award from the Institute of Engineers. And so many others. His research interest includes computer architecture, algorithm, parallel and distributed computing, mobile communication, and wireless network. Today, his topic is meta-heuristic algorithms for intelligent traffic distribution in a disaster situation. Now, I request Professor Bhabani Prasad Sinha sir to start his presentation.
Good morning to all of you, and thank you very much, Dr. Rai, for your kind introduction. I would like to thank the organizer for extending an invitation to me for delivering this keynote talk of today in this METASOFT 2022. In particular to Dr. Ray, because she approached me a few days back to deliver this lecture. So I found it a nice opportunity to tell something, to present something before the audience. Although METASOFT, that particular area is not my own area of work, but I thought that I would talk today about some of the application areas where these meta-heuristic algorithms can be applied. So that's the purpose of today's talk. Let me start with the presentation. For the sake of the time, let me go a little bit quickly to the presentation itself. Can all of you see this page?
Yes, sir.
Okay. Okay. So the title of this talk today's talk is Meta-heuristic algorithms for intelligent traffic distribution in a disaster situation. So this is a typical application area. I think there is some noise coming in. Noise. Dr. Ray, is it okay?
No, it's agreeable. Little bit noise is coming, but it's agreeable, not a problem.
Okay. So basically, as I told that I will address one typical application area, namely this intelligent traffic distribution applicable in a disaster situation where these meta-heuristic algorithms can be used or can be designed. So what do we mean by heuristics? Normally, the term heuristics in the domain of computer science refers to something to find or to discover by trial and error. And the word meta, if you see the dictionary meaning, so that means that it is something about itself, so something going beyond or higher level. The example is, if you look at the metadata, we are all familiar with the term metadata, so which means as information or data about the data. For example, if you have the database in the domain of database, we refer to data about the tables used in the database. For example, the table name, table owner, column details. So on the basis of this information, the database itself can be developed. So that is an information. The data, metadata refers to the data about the data itself. In the same way, meta-heuristics, if you know that heuristics is something to find or to discover by trial and error, then meta-heuristics refers to some master strategy that guides and modifies other heuristics to produce some better solutions. So it is a master strategy for choosing the proper heuristics. Meta-heuristic properties that include the finding strategies for, that is a basic property, basic requirement. Strategies for guiding the search process to find near optimal solutions. Finding techniques that may range from simple local search procedures to complex learning processes. And those algorithms are, meta-heuristic algorithms are usually approximate and non-deterministic. These algorithms use some trade-off between randomization and local search, takes reasonable amount of time to generate quality solution, but without any guarantee of having truly optimal solutions, okay? So the quality solutions is important, and also the time of delivering that solution, so that is also very much important. And these are often based on learning from natural processes happening around. That may be an evolution process, that may be a physical process, or that may be something related to the biological systems. And the examples in this domain, all these, meta-heuristic algorithms, they are like say genetic algorithm based on the evolution. Physical process may be simulated annealing. The particle swarm optimization, the behavior of this swarm and colony optimization, or the biological system may be artificial immune system like that. The different types of meta-heuristic algorithms, if you can, I do not know whether this table is visible to all one, so we can have, so this, I have taken it from some other source. So meta-heuristic algorithms is, that can be say evolutionary algorithms, which may include say genetic algorithm, differential evolution, genetic programming, evolutionary strategy, or the physics-based algorithms that may include simulated annealing, this gravitational search algorithm, harmonic search, mimetic algorithm, swarm-based algorithms like this SU and colony optimization, PSO, the particle swarm optimization, artificial bee colony, fish swarm algorithm, bio-inspired algorithms, namely the artificial immune system, bacterial foraging optimization, the BFO, or dendritic cell algorithm, DCA, or krill horde algorithm, KHA. Nature-inspired algorithms that may include cuckoo search, firefly algorithm, bat algorithm, invasive weed optimization algorithm, and so on. So having such a taxonomy of these terminologies, so what do you mean by these meta-heuristic optimizations? This deals with the optimization problems using such meta-heuristic algorithms. Okay, and optimization is essentially everywhere in real life. Maybe holiday planning, maybe go for the financial investment planning, maybe go for engineering design, VLSI design, or anything, something like that. If you go for internet routing, these days internet routing is very important, particularly the wireless communication and optical communication, or the hybrid wireless optical communication area. This routing of message is very important. Vehicle transportation is, very well-known problem, and so on. So I think our whole life is an optimization one. It deals with only optimization. So what is the objective of this talk? We focus on a specific application area today. For example, the vehicle transportation problem. First, we build a framework to find a near optimal solution to the problem based on some heuristic. Okay, we will see what heuristic we can apply or use. So the applicability of this technique, this heuristic-based technique, to message routing in a wide area network. So that is, so we will actually discuss a framework which will cover two such types of problems. One is a vehicle routing problem, transportation problem. Another is the message routing problem. Vehicle routing, message routing, both. And discuss about open research problems for finding improved optimal solutions based on appropriate meta heuristics covering both types of these problems. So that is our objective today. And yeah, if we just look at the vehicle transportation problem, so some basic concepts, let us deal with those things. And we often hear about the intelligent transportation system. And intelligent transportation system is one of the important considerations in building a smart city, which is a project taken over by globally taken over by the different countries. So, and we need proper infrastructure needed to cope up with the extraordinary situations arising out of a natural disaster. Particularly, if you look at the natural disaster, then we should have some sort of infrastructure to cope up in those under those situations. When you talk about building a smart city or something like that. In particular, evacuation of people to designated self-shelters will be one of the most important requirements. And what happens normally that during natural disaster, that all the vehicles want to be routed to the shortest path. So routing of vehicles to the shortest path may not always be the best strategy, because that may lead to congestion at some points. Everyone wants to go to the shortest path, and that may lead to a congestion, and eventually that will be, not paying. That will be in the other direction. The time will increase. So an optimal traffic distribution strategy is very much needed for such fast evacuation process, and that must be an intelligent one that should guide all these smart cars to be routed in the proper along the proper path. So in transportation network, if you just look at the some basic concepts, the transportation network describes a network structure to allow flow of some commodity. What can be commodity? Commodity can be anything which can flow through the network. It may be the vehicle, commodity may be vehicles for the road network, and commodity may be the messages in a communication network, in a telecommunication system. So the commodities may be the messages itself. So every non-destination node may be a source of commodities generated in a random manner. And this ITS, or the Intelligent Transportation System, that helps to transport such commodities from the source points to their respective destinations in an efficient way. So that is the most important thing, that we have to transport these commodities from the source to the destinations in an efficient way. So efficiency that can be defined depending on the application's requirement. So for example, if it is an evacuation problem in a disaster situation, that we look for the average travel time or the maximum travel time, and so that everyone can get the safe shelter, get into the safe shelter within the specific maximum amount of time. For other cases, it may be some energy or some fuel or something like that. So this all those things depend on the specific application requirement. Route planning in a dynamic environment is termed as the dynamic traffic assignment, because everything is dynamic, the traffic is dynamic. So if you want to do any route planning, then that must be done in a dynamic traffic assignment algorithm. Sending a given amount of a flow from the source or sources to the sinks in the shortest possible time is termed as the quickest flow problem. And in this case, particularly the evacuation of people to the designated self-shelters in a disaster situation in minimum possible time is the quickest flow problem. So we discuss here, as I have already mentioned, about building a framework for solving the quickest flow problem. And as I already also mentioned, that based on this framework, we can solve two applications. One is the traffic management in a road network in the event of a natural disaster. And this framework will also help us having an efficient message routing in a wide area network to achieve the goal of ultra low end-to-end communication latency in 6G networks. Usually the 6G networks, they require the communication latency of the order of sub-millisecond. Now it is several milliseconds, maybe 5 to 10 milliseconds. It has to be brought down to the sub-millisecond region, and for that, some intelligent transportation algorithm is very much necessary. So that's a real challenge. So those are the two real challenges which we would like to tackle through this framework. Okay, let's see. As I have already mentioned, that shortest distance paths for individual commodities may not necessarily provide the minimum time solution due to possible congestion at intermediate nodes. Rather, it is needed to minimize the total average time so that the commodities may reach their respective destination, considering congestion delays at all intermediate points. So we discuss here about a heuristic mimicking the physical process of wave propagation. So that is, here is a heuristic. As I have already mentioned, that the meta heuristics, the heuristics, those are often design based on different natural processes, physical processes. So one of the physical processes is the wave propagation. So we will try to mimic this wave propagation and develop the heuristic. And let us to understand the basic concept. Let us start from a very simple version of this whole problem. The problem is very big. So we consider, instead of a general road network, we consider a grid network. Okay, so grid network where the I mean, all roads are horizontal, vertical here, as you can see, in the form of a grid, and also we consider to start with a square grid. Let us start with this very simple value of this simple version of this problem. Consider a K by K. It is called a Manhattan grid network because it is like the I mean, Manhattan borough of the New York City that has got this type of road structure. So it is often called the K by K Manhattan grid network. And we will consider the there are multiple sources of this traffic, but there is only one destination, namely the home destination is H, as you can see, and the topmost rightmost corner of this grid. So that is the home where we have to reach all. And the traffic, we assume that the traffics may actually be generated at different cross points. What is a cross point? The cross point is actually the intersection of a horizontal and vertical line. So it is the black dots are there, small dots. Those are terms of the cross points or the intersection points. So this every cross point excepting the boundaries is a four-way intersection point. And the traffic generated at each of these cross points, we have to reach, suppose, only one single destination at the topmost rightmost corner, that is destination, home destination is H, and that is the purpose. And here you can see that all these actually, since if we want to start from any point, and if you say that, well, we do not go for any detouring, so everyone will actually reach through the shortest possible path. So I mean, incidentally, this because of this particular structure, this grid structure, we can say that from any node, say any cross point, if you want to reach to the destination point at H without detouring, then there are many possible paths, even with the shortest distance. For example, say if we consider this cross point, say P12 here, okay, you can see the P12. So then from P12, we can reach H by traversing 1, 2, 3 horizontal links and 1, 2, 3, 4 vertical links. So the distance, I mean the orthogonal distance, I mean rectilinear distance, not this, I mean Euclidean distance, but the rectilinear distance from P12 to H is 3 plus 4 is 7. And we can choose many different possible paths without detouring, which will all lead us to H with a path length of 7. This rectilinear path length. So even with the shortest possible path, shortest possible distance, there are many possible paths. You can see that mathematically you can find that this number of possible paths can actually go up exponentially with the number of nodes in this neural networks, the size of the network. So even then choosing the correct path for the traffic from a particular cross point, a particular vehicle generated from a particular cross point will be a big issue, so as to avoid, I mean, congestion or to minimize the congestion delay. So this is the actual problem. So as I told that we try to use a heuristic which will mimic the physical process of wave propagation. So just like if you say that something is generated at P12 and this wave is some energy in the form of wave that will reach H, that point H. So the waves normally travel in the form of the wavefronts. Here also we define these flow fronts. Instead of wavefront, we said the concept of flow fronts are introduced, which are the lines parallel to the main diagonal. So in this case, the main diagonal, as you can see, this dotted one from which is termed as F5. It's okay. And all the lines parallel to this main diagonal, all the dotted lines, as you can see, so those are the flow fronts, different flow fronts. The first, the flow front on the leftmost, bottommost side is F1, then the flow front F2, then flow front F3, flow front F4, flow front F5, F6, F7, like that. So the flow fronts, the wave fronts are actually the locus of all points in having the same phase. And here, the locus of all cross points, which are the same distance from the final destination. So those will actually be constitute the flow front. As you can see, the flow front, say F2. So this has got 2 points, P12 and P22, two cross points on it. So P12 is at a distance 7, as you have already computed, 7 from H. Similarly, P22 is also at distance 7 from H. You see, P22 we can go vertically maybe 3 links, and then horizontally 4 links, so we can reach H. So P12 and P22 are actually at the same distance. So all cross points on a particular flow front are at the same rectilinear distance from the final destination of the home. Okay. So these are the basic concepts. So when a vehicle moves from its source to the destination, the total time of travel will have 2 components. One component is the queuing delay at each cross point of the grid, and another component is a link delay, that is time to traverse a link connecting 2 adjacent cross points. So our objective is to minimize the total delay of the traffic flow. So not only for the single vehicle, but for all the vehicles generated at different points. And that every vehicle, if the individual vehicle, suffers from 2 types of delays. One is the queuing delay at each cross point of the grid, and also another is the link delay for traversing all the links it has to traverse to reach the final destination. So then if you want to minimize the total travel time for all the vehicles, then for each vehicle we have to find out the value of this queuing delay and link delay, sum of this, and then to minimize it. So that is the overall problem. Let us assume the MM1 queuing model. MM1 queuing model is the Markov. So there are traffic generation process that follows Markov process, that is a Markov process. Then traffic servicing pattern, so that is also Markov process. And then there is only one server, so namely that one traffic controller, so that will actually, when a particular only one vehicle can move along the intersection point when it comes there. So MM1 queuing model is assumed. A cross point Pij on flow front. So we denote this cross point at Pij on the flow front Fj. So for example, if you see this flow front, say F3, so it has got the cross points P13, P23, P33. Flow point F4, it has got the cross points P14, P24, P34, P44, like that. So we have marked these cross points Pij on every flow front Fj. And we assume that this cross point Pij has a new traffic generation. New traffic generation means only at that point, which is of value lambda ij. And every cross point is assumed to have a uniform service rate of mu with lambda ij much less than mu. Traffic from a source to the destination is assumed to move along the shortest distance paths. So no detouring, as I have already mentioned. And even with no detouring, as I have mentioned, that there are, if you try to find out the total number of possible paths, even the same shortest distance from any cross point to the final destination, say H, then it will be, it will grow exponentially with the size of the grid. So as queuing delay, we have to compute. So at each these cross points, say Pij, through which the vehicle passes every flow front, the queuing delay is some constant A over 1 minus lambda ij by mu. So that is that comes from this expression from the queuing delay, where lambda ij is the total traffic arrival rate at Pij, and A being some constant. So at each cross point Pij, okay. So link delay alpha is assumed to be same for each link. So this is okay. So that if you consider with lambda ij part, then it is okay. But when it comes to lambda ij is actually the traffic generated at that particular cross point. But the problem will be more complicated when you have to consider the traffic coming also from the other cross points. So that will all pile up at the same cross point Pij. So eventually this lambda ij will be changed to some other value, which we will see later. The link delay alpha is assumed to be same for each link. For the time being, let us assume the link delay is same, so that it is a constant thing for each of these vehicles from this cross point Pij to the final destination. So finding the globally optimal solution is very difficult and time consuming, even with all these simple ideas. Simple ideas means what are the assumptions? We assume that the road is actually a grid road, it's a square grid. The traffics are generated at in a random fashion following Markov process, and the servicing pattern is also Markov process. Everything is done, and still we find, and the link delay is assumed to be same for each link. So only queuing delay is to be minimized, and queuing delay for all the vehicles. So, and if you want to find the globally optimal solution, you can see that it will be very difficult and time consuming. We do not get any handle how to solve these things. So rather, we use a heuristic here for a quick near optimal solution, because we have every solution, the engineering solution should be practical enough. That means the solutions must be obtained. If it is not an optimal one, it should be at least near optimal, but with a reasonable amount of time. So this heuristic what we use here, that find a locally optimal solution over each individual flow front. So that is the thing that we divided this whole concept of flow in terms of these flow fronts, following this, mimicking this idea of wave propagation along the wave fronts, and we try to minimize this delay over each individual flow front, minimize the traffic flow delay through each individual flow front. So that is definitely a local optimality, but we do not know what will be the global optimality. Let us see. There are two phases of traffic flow. One is the expansion phase, where the number of cross points on these flow fronts actually increasing, gradually increasing. You see that if you see this picture here, then from F1 there is only one cross point, F2 has got two cross points, P1 to P2, F3 has got three cross points, P1, 3, P2, 3, P3, F4 has got four cross points, F5 has got five cross points. So up to F5, the number of cross points are increasing, and we call that as an expansion phase. But beyond F5, you see that F5 has got five cross points, 1, 2, 3, 4, 5. And F6 has got only four cross points. So from F5 to F6, the number of cross points will actually decrease, and that we call as the contraction phase. That happens from F5 to F6, F6 to F7, F7 to F8, F8 to F9. Okay, so the number of cross points will gradually decrease, and eventually, when it comes to this corner point here, the topmost rightmost corner point, we will get again only one cross point on the flow front F9. We started with the F1 where there was only one cross point, and then end up with also F9 where there is also one cross point. So at any cross point Pij, traffic is directed in two possible directions. If we assume that there is no, okay, come back to this diagram again. If we assume that we do not go for any detouring, so we'll direct all the vehicles towards this shortest possible distance. Then from any cross point, we can only direct a vehicle towards the right or towards the up. So there are only two possible links. Out of these four links, so we will use from any cross point, only two possible links will be used to direct a particular vehicle, a specific vehicle. Maybe the first vehicle will go along the right direction. The second vehicle, we may think that we will route it to the along the uplink. Third vehicle may also go along the uplink, and the fourth vehicle may go possibly along the right link. Like that, we can distribute it. But from every point, so there are two possible ways. So the number of possible ways you can distribute a particular vehicle is also exponential with the size of the grid, because it is 2 times 2 times 2 times 2. So that will be many. So choosing the correct path for every vehicle is a real challenging problem, and that is the point of our discussion, how to optimize it. So what we want to do, that at any cross point Pij, traffic is directed in two possible directions. One is horizontally, maybe towards right, or vertically along up. So fraction of traffic directed along the right link, we term that as Fij, and remaining 1 minus Fij, this is fraction, is directed along the uplink. Okay, so the red part is actually along the uplink, and the blue part is along the right link. So traffic arrival, so you can see that from every point here what is happening. Traffic arrival rate at Pij is Xij. So look at this Pij part here. This traffic arrival rate is Xij. It is coming from all other points, all other cross points below it. Okay, because all the traffic are actually flowing throughout reach this destination at H. So from the traffic from the cross points generated at all the traffics below the flow front Fj, so part of that will come to this Pij, and that is Xij. Okay, traffic arrival rate is Xij. Out of this traffic which is arriving here at Xij, some part is Fij part is actually directed along the right. Similarly, if you see this Xi minus 1j at Pi minus 1j, so that 1 minus Fi minus 1j part is actually directed along the uplink here. So both these parts, then Xij times Fij and Xi minus 1j times 1 minus Fi minus 1j, both are added to the new traffic generated at Pij plus 1. So the that is, what is the new traffic generated at Pij plus 1? That is lambda ij plus 1. And that will be the total traffic at Pij plus 1, which is termed as Yij plus 1. So that is the thing what we have to model. The total traffic at cross point Pij plus 1 is denoted by Yij plus 1, where Yij plus 1 is equal to Fij Xij plus 1 minus Fi minus 1j Xi minus 1j plus lambda ij plus 1. Okay, that we have to also add because that is the new traffic generation. So once we know that this is our Yij plus 1, the total traffic at Pij plus 1, so then the waiting time at this Pij plus 1, that is with Wij plus 1. We already told about the wait time at a particular, no, that is some constant A divided by 1 minus lambda ij by mu, something like that. So here the total traffic is not lambda ij, but it is Yij plus 1. So that, and corresponding to that, this Wij plus 1 has to be actually changed. What is Wij plus 1? That will be some constant A into Yij plus 1 divided by 1 minus Yij plus 1 by mu. And if we just divide it by the averaging part, so that is divided about the total traffic at all the cross points with at the flow front Fij plus 1. So at flow front Fj plus 1. So if you sum it over all i's, it will call that as T. Capital T is the total traffic over the flow front Fj plus 1. So this will be something like this mu by T into this sigma part, where T is equal to the sigma Yij plus 1, the total traffic generated from all cross points on the flow fronts F1 to Fj plus 1. That is, T is equal to sigma of all these, say I is equal to 1 to j and j equal to 1 to j plus 1. So all these values, this is the value of the T. So basically we have been able to identify the function which is to be optimized. So this is actually the function, the average delay through the flow from j plus 1, Fj plus 1. So that is Wfj plus 1. So that we have been able to identify, and that is to be optimized. Note that that is to be separately optimized for local optimality at the flow front Fj plus 1. So given the traffic distribution in the expansion phase, what we can do, given the values of A, mu, T and T, the T greater than 0, Wfj plus 1 can be minimized properly by properly adjusting the Wij plus 1 values. So we can formulate the optimization problem in a very nice way. So suppose we denote this Yij plus 1 by some Yi, to simplify this, and denote j plus 1 by n, and eventually it will look like some optimal, some function to be optimized. You see that this is a nonlinear optimization problem. The y1 divided by some function of y1, y2, yn, the y1 divided by mu minus y1 plus y2 divided by mu minus y2 plus dot dot plus yn by mu minus yn, and that is a constant optimization subject to the constants that sum of all these y1 plus y2 yn is equal to capital T, and each of y1 is actually greater than equal to 0. Traffic cannot be less than 0, and y1 is always less than mu. Y1, y2, yn all are actually less than the mu, the service rate. Okay. Well, this is only an optimization problem, and we can really solve it. There is a problem, and if you see this, if we solve this, then we really find that the average queuing delay at any given flow from Fj plus 1 will be minimum when the total traffic over Fj plus 1 is uniformly distributed over all the cross points on Fj plus 1. So the summary of the optimization problem is that Fj plus 1, the traffic delay through this Fj plus 1, that will be minimum. Traffic delay means here always the average queuing delay, because link delay is same for each of the vehicles, so that is a constant part. We just forget about that. For constant part for all the traffic reaching Fj plus 1. Okay, and from Fj plus 1 to the destination. Okay, so that is constant for all the vehicles, each of the vehicles. So that part can be eliminated. So only average queuing delay is minimized. So if it is minimum, then if the traffic over all the cross points on Fj plus 1 they are equal, then only this will be minimum. So that is, most of us can intuitively think that, well, that is the case. Okay, yeah, but that the formal proof is really very I mean that's not so simple. Formal proof is a little bit involved and complicated. People will not accept if you say that, well, it will be same at all the cross points. But why? That has to be formally proved, and that can be formally proved. That has been proved in the literature. So what do we want to show? There is a problem. Okay, there is a problem with this result. Problem is like this. Let us see that we have got this just a simple situation. We have got these three flow fronts F1, F2, and F3. And F1, the one cross point A has got the lambda 1, 1 that is a 0.4, and this lambda 2, 3, this cross point B on the F3, so that has got the new traffic generation of 0.8, and no other point that is no traffic. So all other points have got zero traffic generation. Now, so from the point A, actually the traffic will be diverted equally in both directions. So here in F2, the traffic will be 0.4 is divided in 0.2 and 0.2 in two parts. And then if you see the total traffic over flow from F3, that will be this 0.4 plus 0.8. So that will be 1.2. Now if it is 1.2, and that has to be divided equally among all these three cross points. There are three cross points on F3. So each cross point should receive 0.4. But you see that already this cross point B, this here, that is having the traffic 0.8. We cannot actually move it to the other, distribute it to the other cross points. And this is the maximum you can get at other cross points is 0.2 and 0.2. So this is actually the result, although the result requires that each of these cross points on front F3 should get 0.4, 0.4, 0.4 traffic. That is impossible. Okay. So then what is the way? So what to do? Let us assume a function, suppose if you have a function, say just calculus, ax square minus 6x plus 10, fx is this, and try to find the minimum of fx within the intervals of 0 to 2. We can see that this particular function has a minimum, true minimum at x equal to 3. Okay, so x equal to 2 is not the global minimum. I mean this within the region 0 to 2. But what we can say that in this region, so 0 to 3, that the function is, or 0 to 2 at this closed interval, the function is monotonically decreasing, and so the whatever we get, even from 2 to 3, this is monotonically decreasing, and so what we can say that this function value f2 is the minimum over this interval 0 to 2. Exactly similar idea we can borrow here, and we can say that we can easily check that the yij plus 1 is a linear monotonically increasing function of fij values. Our ultimate objective is to find the fij values. So yij plus 1 is a linear monotonically increasing function of fij values, and because of such monotonicity, and wij plus 1, the queuing delay is a monotonically increasing function of yij plus 1. And because of that, one can say that if any fij value needs to be negative, we assign its value to 0. So actually what happened that if you look at the previous example, this previous example situation, then we needed something like negative value for I mean more than one value. Say the traffic from here, it should go to be doubled twice. This should go also twice, and I do not know what will happen. So this is 0.8. We cannot actually make it 0.8. So maybe something has to be done. So this is not possible. So basically, what will happen that a result will lead to some fij value which will be more than 1 or less than 0. So if any fij value needs to be negative by virtue of the optimization problem, we can assign its value to 0, the limiting value on the left side of the interval 0, 1. And if any fij value requires to be more than 1, then we assign its value to 1, the limiting value on the right side of the interval 0, 1. And if we do that, again, there is one kind of approximation. This is a near optimality requirement. So with such assignments, we finally obtain the minimal possible queuing delay with all values of fij within the allowed range of 0, 1. Fij can be either 0 minimum and 1 is maximum. With these possible values, we can get only the allowed minimum value. So we can consider all possible values of xij. So when xij equal to 0, then both the rightward and upward traffic from Pij to the flow from Fij may be 0. So to keep our idea fixed in such a situation when xi is equal to 0, we decide to set the corresponding Fij value to 0 without affecting the result. So with all these things, we can possibly find some, I mean, Fij values. Okay, these are complicated formulas. I just skip those things. Those are not required for our talk, but just to get an overall idea, I am showing you just for a glance. And then in a similar way, we can go for the contraction phase when the number of cross points on the flow fronts will be gradually decreasing. And in the same way, we can find the formula for the Fij coefficient. So what is the importance of this particular rule? The importance of this particular study is, so far, what we have just now discussed, that we can actually find some locally optimal solution over each flow front. And once we solve this solution, solve for the optimality, that can be solved for optimality in order in, I mean, say k square time, if k is the size of the grid, and then those can actually be be stored in the stored in some memory, and those can be used by any vehicle. Okay, I am coming to that. First, look at the algorithm. So we can, design the algorithm. Here, this algorithm is very simple, and where we are using some two algorithms. Execute algorithm 2 for the expansion phase, algorithm 3 for the contraction phase, and algorithm 2 and 3 are still computing this total traffic during the expansion phase. These values Tij, and also these with those values Fijs are computed here in algorithm 1. Okay, they are actually finding the right traffic part, and right, once we get the right traffic, then we can get also the up traffic. Okay, so that is the overall purpose. Algorithm 2 or algorithm 3, those are being used in executing algorithm 1. So that algorithm actually helps us to find these values of the coefficients. And then if you know, if a particular at intersection point, if you say that the optimal coefficient for directing along the right link is say 0.6, that means then every vehicle can actually run, the smart car can actually run a some algorithm which will generate this uniform random number, say between 0 and 1. So if the random number generated is say 0.5, less than 0.6, then we said, okay, this particular vehicle will move along the right. If the random number generator actually generates the values of 0.7, more than 0.6, okay, then direct it along the uplink like that. So within say 0 to 0.6, if the random number generator is within 0 to 0.6, then that vehicle will direct itself along the right link. And if it is between 0.6 and 1, then that vehicle will be directed along the uplink. So this application is very simple. And also, this will help from, this will be aided by the information from these roadside units. The roadside units will actually collect the data about the new traffic generation rate at each and every intersection point of the cross point, and those will actually be fed to the system over the particular time window, and that will be used by the central computing system, or maybe in a distributed manner, and those values will be used to compute these traffic distribution factors, which will be used by every vehicle in the next time interval, next time. So the application wise, it is very easy, and it is practical. The only thing is that what is the effectiveness of this particular algorithm. Okay. First of all, let us see. Algorithm 1 follows the previously obtained results, and it starts executing in a distributed manner at all cross points of flow front F1, and continues to execute for every flow front. And as I told, the new traffic generation rates, lambda ij, at all cross points over a time window are sensed by the RSU or the roadside units, and these lambda values are used by the algorithm to compute the traffic distribution factors during the next time window. Okay. But there are more, and the real life cases are much more complicated than this simple model. So we have to sometimes think about the detouring of vehicles, and we have to also consider the link delays are not same over all the links. That variable vehicle speed may be in the link delay, even in this grid network. So if you consider the detouring of vehicle, then you can see this diagram. I just show you the diagram. So this blue part, as you can see, blue lines, the dotted lines, if you can see that blue lines. So those are actually detours outside the normal grid. So then those are actually all reaching this cross points. The final destination point H, home, along these detour paths, the blue paths. And this is a kind of, if you want to detour by just one level, that means you go along the right here and again come back along the left link, so that you reach here. So that every detouring involves actually 2 extra link delays. Okay, that's fine. And if you have detouring of multiple levels, so it's 2-level detouring, that will require 2 level towards right, 2 links, and then again coming back 2 links along the left. So 2 plus 2, 4 links. So basically, if you want to detour, then the congestion delay, delay due to the congestion can be reduced at the cost of some increased link delay. So there we can actually again write the optimization, formulate the optimization problem in view of some k-level detouring, and which one is, which value of k will be most appropriate. So the detouring is particularly important because when the vehicles actually come nearer and nearer to this destination home, then there will be a lot of vehicles coming, and that will cause the number of cross points will also be reduced. So then that will be actually causing more congestion delay. So for those things, to avoid that or reduce that congestion delay, detouring is very much essential particularly near the final destination point, so that we cannot really over rule or just forget it. Okay, that has to be considered. And we can consider in the detouring. I have also already mentioned all these things. Considering detouring, we can formulate the optimization problem accordingly. And if you consider this variable link delay, the variable link delay, the links can be, we assume that all links are of equal length L, but variable speed, vehicle speed may be variable because of the amount of traffic along that particular link. And if you consider follow the Bureau of Public Roads that function, the link delay alpha can be expressed as some constant t0 plus some constant phi into eta to the power 4, where eta is actually the rate of traffic flowing through that particular link. Actually, phi, this constant phi, that depends on the maximum vehicle speed specified for that link. So it may be normally, say, if it is a 50 kilometers per hour, or so that is 30 miles per hour. So, and based on that, the phi value of phi can be accordingly fixed. Okay. And if we assume this variable link delay, then again the modeling can be done. I'm not going into all these details, so that only for the ITS people, important for the ITS people. And we can definitely find a similar optimization problem and get the values accordingly. So basically, what I wanted to say, that if you consider this over and above this simplest model of K by K grid with no detouring and all uniform link delay, we can gradually include the complications like the detouring is possible, or this vehicle speed along a link can also variable, and even we can get even we can formulate the optimization problem accordingly and find these traffic distribution factors, which will be pre-computed and used by each and every vehicle. But these are all based on the heuristic. What heuristic? That we are actually minimizing the traffic over each individual flow from separately. Okay. Lower. That was up to K by K grid. Now the question is that what will happen to the rectangular grid? Okay, if you consider the rectangular grid, so a rectangle can be of two types. Of one is, say, as you can see, this number of horizontal lines is more, vertical lines is less, and here the number of vertical lines is more and horizontal line is less. So if it is an m by n grid, then m can be less than n or m could be greater than n. M by n means m horizontal and n vertical lines. Okay, and by assuming still the topmost and rightmost corner of the grid, rectangular grid is also still this home, that is a final destination point, we can similarly form the optimization problem. I'm not going at all with all these details, but it can be very well determined, because for that we know, again we have to consider this expansion phase, and there will be some unchanging phase. That let me explain only that, what extra complications will come here. So if you consider this particular rectangular grid, where m is the horizontal number of horizontal lines is more and the number of vertical lines is less. Then you see that F5, consider these two flow front. F5 has got how many? 1, 2, 3, 4, 5 cross points. F6 has also got 5 cross points. 1, 2, 3, 4, 5. And after that, F7 has got only 4 cross points. So there is a phase in which the number of cross points on the flow front will not decrease. So that will remain constant. So that is called the unchanging phase. So what we considered in a square grid, one part was there that the expansion phase, the number of cross points on the flow front was increasing gradually from one flow front to the next one. And in the contraction phase, it was decreasing gradually from one flow front to the next flow front. But in this case, the extra complications is introduced in the form of an unchanging phase, where the number of cross points will not change when you go from one flow front to the other flow front. So the optimization problem should be separately formed for this unchanging phase. Nevertheless, it is very much possible to design to formulate the optimization problem for each of these expansion, unchanging, and contraction phases, and find these traffic distribution factors over each of these flow fronts for time optimality of the individual vehicles. Okay. So far, so good. Now let us quickly. So I think I can go to this next one. So I have already said. So if you see the real life road network, so you can say that the real life road network may vary drastically from all these things. Yes, that is true. So we can take the case of this Manhattan borough of New York. So this is the part of this. I mean their map. This is the whole map, and we took one part. This is the green part is actually one part here, and here we can see that yes, there are some deviations. Some of the links are actually not present. Some of the links are absent. So in this figure, you can see missing links. Those are represented by this some dotted lines. Some dotted lines, this here. These are all missing links. So when there are some missing links, then naturally we cannot consider it as a continuous grid. So that really induces the partitioning of the whole network in terms of the sub-networks, several sub-networks. So this particular network, which you consider that it is on the left side there is a Park Avenue, right side is First Avenue, and the top side is 96th Street, and the bottom side is 91st Street. So, and then you can see that there are some partitioning of these on different subnetworks, different of types. We define the subnetworks of 4 types. We can define some subnetworks of the 4 types. Some cross points may have one of the links, that is right link or the uplink absent, while some may not have either of these 2 links. Okay, so that will actually have the, depending on the boundary, some boundary node of the subnetwork, if that has got both the links absent, the right link or the uplink, or one of the maybe the right link absent, uplink present, or uplink right link present but uplink absent, then or both the links are present. So based on that, there are 4 different kinds of types. So type 1, each of the 2 boundary cross points have both the rightward and upward links. So that is one subnetwork type. Type 2 is that one of these right boundary of the cross point, right boundary has got only, does not have the rightward link, and left boundary does not have the upward link, like that. So in this way, without going into the details, there are 4 different types, and for each type of the subnetwork, again we can similarly formulate this optimization problem and design the algorithms accordingly to find this traffic distribution factor. So this is the traffic distribution algorithm, which uses all the results based on this type 1, type 2, type 3, and type 4. As you can see, type 1, type 2, type 3, type 4. So far so good. So and we can actually run the simulation. So we can see that, well, this is the real life experiment. So you can see the simulation performed from this real life scenario using Sumo. Sumo is a very well-known simulation software in this transportation system. If you consider the maximum vehicle speed is 13.9 meter per second. Okay, it is a weird value. It is just corresponds to 50 kilometer per hour. Okay, 50 kilometer per hour, 30 miles per hour in USA. So if the 50 kilometer per hour, if you multiply it by 5 by 18, so that will be 13.9 meters per second. So every link connecting 2 nodes in the network is assumed to be of length 300 meters. So some simulation parameters were used. Different types of vehicles were also used. And then, so I have to quickly wrap up. So what you want to say that, well, this is very much doable, and it can be really compared with the existing results. And when you compare these existing results, we can see that I mean, sufficiently encouraging values are used. Final extension to all these ideas to the special cases that so far we consider only one destination point at the topmost rightmost corner. But actually, in real life, the evacuation center or the safe shelter may not be at the corner point of any, I mean, at one end of this city, but it should be usually somewhere in the middle of the city. So if it is actually non-corner city, so why did you consider a corner point? Just for the sake of, I mean, our ease of formulating, forming a model and analyzing the particular situation. But when you come to the non-corner destination point, since we have already got the basic things, built up the basic things, then we can also think about the non-corner destination point. That will add to some more complications in the form of different types of flow. Okay, so again, I am skipping all those details. If anybody is interested, he or she may contact me for details. And what is that? There are different flow types. Okay, so there are 3 flow types. So that will actually induce 3 flow type 1, when all cross points on a flow front receive traffic from at most 2 incoming edges. Then flow type 2, a cross point in a flow front receives combined traffic along 3 incoming edges from 2 neighboring subnets. And the flow type 3, when each of 2 boundary cross points of a flow front receives combined traffic from both neighboring subnets. So actually, you can see that the in that case, the flow fronts will be like this. Those will not be a planar flow front, but as you can see that some flow fronts will be the square type of thing. So this is their final home, this destination, say S64. So then around that home, then we will have the square of, I mean, at distance 1, square flow front at distance 2, like that. And finally, you come to this flow front, which are not linear, but which are intersecting. So these are linear flow front. But as you say here, these flow fronts are no longer linear. So they are in some 2 neighboring flow fronts from 2 neighboring subgroups, they are intersecting. So there are all these complications will now arise. And fortunately, all these problems can be tackled in a nice way to formulate the final optimization problem. Okay. So finally, what we can see, the optimization problem for each of these flow types can be easily formulated, and optimum traffic distribution factors at each trust point can be computed by solving these optimization problems. End result. So we can actually get this traffic distribution algorithm for this route vehicle. So that is the final algorithm, and that will use in the if we again look at the simulation results, so that will be very much encouraging. But the basic question still remains. So what about the most general case? So we have to design finally the meta heuristic algorithm. So this is a kind of heuristic what you use following this flow along the flow of the waves. Waves are like flowing like that through a wave front, and here also we are using these flow fronts. The vehicles are moving in the form of step by step from one flow front to the next in that way. And we also consider this optimization over individual flow fronts. So in the most general case, what we guess that optimal traffic movements can be computed by some meta heuristic algorithm. Okay. And the computation time is an important performance parameter for its effective uses in real-time traffic management. We cannot actually afford to spend a lot of time for computing the optimal traffic distribution. Computation time with such techniques, again, as we can envisage through all these studies, that may depend on specific traffic generation patterns. So some actual cross points have the habit that, well, the traffic will be generated at a very heavy rate during these hours of the day, these hours of the day. Some will not have this that property, something like that. So every traffic generation pattern has a specific effect on this overall computing such process, minimality, the global optimality, and also the computation time. In any case, the global optimality we have not been able to find through this model, but we can use that thing to find the global optimal by using some meta heuristic algorithm. So the computation time with such techniques may depend on the specific traffic generation patterns over different time windows, and naturally that will lead to some sort of learning process in between. So if you can actually learn from the behavior, and if we know that this is the possible pattern, and that can be taken care of in our meta heuristic algorithm. So what can be future research directions? We can think of definitely application of a suitable meta heuristic algorithm. For example, selecting from among the above heuristic, that is one heuristic that may work for a particular traffic distribution. Say in the Manhattan cities, that may work very well. It may do provide very good result with reasonable time. Within a millisecond, you can get the results. Or you can have these swarm-based algorithms like particle swarm optimization or the ant colony optimization. This will be particularly useful because the ants or the particles, so they actually follow the minimality in some form or other. Okay, so we can actually learn from that process. And the learning is also very important. If you know the traffic generation pattern, and that can be used by these PSO-SU algorithms, and that can really help us minimizing the total amount of computation time for finding the global optimality. So for obtaining the optimal traffic, this is the objective, that we have to obtain the optimal traffic distribution factors within reasonably small time. It is definitely the global optimality is very difficult, so it will be pretty close to the optimization, but at least that should be an acceptable engineering from the engineering point of view. It should be an acceptable optimal solution within a reasonable amount of time. And so this is I would say this is a rich area of research in this particular area. One can really devote a lot of effort in that. The basic models are all fixed like that, so we can possibly start with these all these the formulation of these optimization problems, and using that model we can further work on. We can also have this machine learning in the training part on the different traffic generation pattern, and find a very good effective algorithm, meta heuristic algorithm. We can do the experiments with some real life data for performance evaluation compared to the existing dynamic traffic assignment DTA techniques. And finally, we can extend this whole thing to multiple destination points. So far, we have not considered more than one destination point, only one destination point. And as soon as this model has not considered so far, so as soon as we add one more destination point, the scenario will be more complicated. And more than two destination points, more and more complicated. So in general, if you have multiple destination points in the to reach, and the overall time has to minimize, that's a real challenge. And that is a very good topic for research on the meta heuristic algorithms in this particular area. And we can, once we are successful in that with multiple destination points, then we can apply the same technique to other types of commodity flow problems, like the ultra low latency message communication in 6G and future generation networks. Messages can start from any node and go to any other node. So when there is a multiple destination point, so each node can be a potential source for generating a message. Also, a potentially it can also receive some message. It may be receiver, potential transmitter, potential generator, potential receiver. So if we can solve that problem for the multiple destination points, it can be very well applicable, be applied to the communication, message communication domain. And there, not only the time, the computation, I mean, today's requirement is, along with the time in the communication field, we are also interested in optimizing the energy, and also the energy as well as the high speed, the time and the energy, particularly optimal energy, high-speed data communication in computation-intensive edge computing environments. So those will be another potential application area where we can use all these results. So we can see that there is a rich, list of these research areas, particularly in the area, domain of the meta-heuristic algorithms. So finally, let me conclude that what we did discuss so far. We discussed about optimal distribution of traffic in a rectangular grid, because time is already up, and or grid-like network with some missing links for a single destination at one corner through local optimization over individual flow forms. We extended this idea to consider more general cases with variable link delays and detouring of vehicles to reduce congestion, and also a non-corner destination point. We applied the basic idea to real-life city road networks, not necessarily grids, showing significant reduction of average travel time of vehicles, and identified some future research areas in designing optimal traffic distribution algorithms based on meta-heuristics. I guess I should stop here, and thank you very much for your attention. And I'm not sure whether I have done the justice to this whole area of this conference, theme of the conference. This is what I could do. Thank you very much.
Thank you, sir, for your nice presentation. If anybody having any doubt or any question, they can ask. The audience present here, if you have any question, you can ask to sir. Okay, if there is no question, then on behalf of the organizing team, METASOFT-2022, I would like to thank Professor Bhabani Sinha sir for an excellent presentation. Really, your presentation makes this conference very meaningful. It's an application of meta-heuristic algorithms for intelligent traffic distribution in a disaster situation. Really, this is very much helpful for us, and also you suggest some future research area that I hope that will help to our participants. Thank you all. Now our next session will start at 11:30 for the paper presentation. Thank you, sir.
Okay, thank you very much, Dr. Ray. Okay, I am not sure whether that was really interesting to all of you, particularly in this domain, the people working in this domain. I do not know.
Yes, sir, it's very interesting area, and the slides you have already shared with me, I'll share with all the participants if they need one.
Okay. Okay.